A prime number, yes, exactly, is a number, it's a natural number that can only be divided by itself or 1. So McGregor's definition was close, but it didn't include the word only, and that's pretty important. So otherwise, like anything works. Examples, Anna threw out the example of 13 was the number you threw out?
19.
There's some other ones, like 19, like 3, like 5, and
7.
so on. You can continue to think some more on your own.
So, pretty much any natural number.
That can only be divided by itself or 1.
Oh. Oh, well,
right? So like 4 doesn't count, because 4 can get divided by itself and 1, but also by 2. So 4 does not count. Well, there is one exception to this. Just something to note down, that 1 is not prime. 1 is its own, kind of its own thing. It's too special to be either prime or composite. It's just 1. It's It's called the unit element. It's also called the I totally forgot this word last hour too. Identity element. There we go. It's also called the identity element in here, but you don't need to know any of that. We do know it's relatively important for down below that we don't consider 1 to be prime. It's just its own thing. Okay, so those are primes. What do you think composites are, Riley?
Numbers that 2 numbers can multiply.
Natural number that, how about something other than 1 in itself divides into evenly? So you've always got 1 in itself, and then maybe there's others. So examples of composite numbers.
24.
Okay, we're going to just knock off A and B there. That's good. 24 is certainly composite. Any even number that's not 2 is composite. Why is that?
Because you can multiply something.
My claim is that every even number that's not 2 is composite. And why do you think that is?
But you can multiply 2 times 4. Oh, 2 divided by 2.
Because if it's even, what number has to go into it?
2.
2. So like 10 has to be composite because 2 goes into it. Right?
Well, 2 would be composite because 2 then minus the same number.
Sorry, what's that?
For prime numbers, is it any odd number that doesn't end in 5?
How about 27? There are examples of others, yeah. That's a good guess, though. For the lower ones, it's pretty close, but as you move up, it's more sporadic. We can also note these are just non-primes. So these actually divide the numbers into 2 cases. You're either prime or you're not prime. And if you're not prime, we call you what's called composite. Yeah, Alex.
So would all even numbers be composite and odd?
Okay, well, let's think about that. So are all even numbers composite? 2 is not. So anything except for 2 is composite. That is a fact. So are all odd numbers composite?
No, 60.
Are all odd numbers prime? And I think the one I threw back at Mitch was an example. 27
60.
prime?
I'm going to knock out C.
yeah, 15 is also composite because 3 and 5 go into 15. 27, 3 and 9 going together. Another good one about like 51, 3 and 13, or 3 and 17. There are a lot of odd numbers that are still composite. Primes are pretty special in that they don't just come up regularly.
I'm gonna knock out C. You don't say that.
Well, okay, so Riley wants to knock out a couple of these examples. So we've already basically done A and B together from the little examples up here. 19 is certainly prime. There's nothing other than 1 and 19 that goes into 19. 24, that's a composite number. It's an even number. Whoops, is composite. And then if it's composite, let's write a pair of numbers that multiplies up to 24.
9 and 7.
9 and 7 do not multiply to be 24. Hallie? 6 and 4 certainly multiply 24. There are others, and you can dream up some more, but 6 and 4 is certainly one pair.
4 and 6.
4 and 6 is considered the same pair as 6 and 4. Okay, 12 and 2, there's a list. If you already haven't, Riley started on number C there, and why don't you guys do both numbers C and D on your own? 9 and 7 is a pair? Did anyone get a different pair than 9 and 7? Mitch?
21 and 3.
21 and 3 also works?
Hold on, I'm thinking about this. What if you
For number D, Anna, what'd you get? Prime, certainly. What you can go through very systematically and just start taking 37 and start dividing it by all the numbers that are less than 37. Once you get to halfway to 37, if you haven't found one, then you can quit. So you can stop there. And I believe if you try that method, you find that 37 is in fact prime. Okay. So this should be a review. I think the next section is going to be a little bit of a review too. So we're going to take this idea of prime versus composite and extend it just a little bit more. So there's a really important idea in mathematics, specifically in something called number theory, that deals with, that talks about what kinds of numbers and how you can break numbers down. And it's this thing called the fundamental theorem of arithmetic. And it says the following. It says that any natural number can be written uniquely as a product of prime numbers. Okay, what does this mean?
Is this saying that 2 primes equal another prime?
No, not quite. What this is saying is that any positive whole number, that's a natural number, so I can take any one of those things I want, and I can always rewrite it I can rewrite it as just the multiplication of a bunch of smaller prime numbers. Moreover, not only can I do that, but there's a unique way. And if I say there's a unique way, what does that mean?
It's special.
Not just special, the only way. There is one and only one way to do it. And you can do it by multiplying prime numbers together. So whether the number is a prime number, whether it's a composite number, you could always take all of these crazy composite numbers and rewrite them as just a bunch of smaller prime numbers that have been multiplied together, is what this theorem is saying. To justify this, we need actually a lot more like crazy high-level mathematics, but the result is pretty nice. the result we can actually use to our advantage. So by doing this, we can do something called prime factor. And when we prime factor, that's going to be the process of breaking down a number into its prime components. So we're going to take a big number and we're going to break it down to a bunch of smaller things that all multiply up that make this big number and all the component parts. And all those component parts will be these special prime numbers as we go through. There are a lot of ways to do this. In years past, you may have used something called a factor tree. And I've got an example of a couple of factor trees over on the sideboard over there for actually two of the numbers we're going to break down, if you remember those. We're going to do it without the tree version, but it's going to be the same type of process. Okay, you should have seen this in many years of past. Okay, so we're going to start relatively easy. We're just going to take these and we're going to break them down into a bunch of prime numbers multiplied together. So 75. Well, how do I do this? Well, what I recommend doing is starting with a prime number you know that goes in and divide it. So note that 5 goes into 75. So 75 is equal to 5 times what? What times 5 is 75? You can answer that question by just using a calculator and dividing. I think we hopefully can agree that it's 15. 15. Okay, so now we start over, but with the new composite number we got. So, the new number that came up. So, is there any prime numbers that go into 15? 5 again. So we could write this as 5 times 5, and then 3 times 5 is 15. Can you break 3 down anymore? No. The final answer, we're going to write this in standard form. And the standard form for this is going to write the prime factors from least to greatest. And instead of writing out all of the same factors, we're going to use exponents to combine like things. So instead of 3 times 5 times 5, I'll write 3 times 5 squared. So 75 is the same as 3 times 5 times 5. And you can always check your answer. Just take a calculator and just multiply out 3 times 5 times 5. And with any luck, the answer will be exactly where we started, 75. The tree method is a little more visual. And if you want to use the tree, go right ahead. There's no problems. Note that the answer to our problem, that the prime factorization for the tree is just the roots of the tree. So when you run out of things to break down, the roots of the tree are the prime factors. If you use a tree diagram. And you can. That's better for you. Use a tree. It's great. If you don't want to use a tree, you don't have to either. But kind of nice. Let's see. I did 242 on the sideboard over there, so I'll skip the C and you can do B on your own. So 242. Let's see. I noticed that 242 is an even number, so I'm going to start with 2. I'm going to start by trying to divide out a 2. And 2 times 121 is 242. Okay, and then there's a number that goes in the 121. 11. You should hopefully already notice that 121 is a special kind of number. Remember what this number is called, that a number times itself is 121? What do we call those special kinds of numbers? Perfect squares. This is a perfect square because it's 11 times 11. Oh, okay, so there's a 2, and then there's 2 11s. The answer is indeed 2 times 11 squared. So with that, I'd like you to try example B on your own here and see what you come up with. So we'll start with about 2. 2 times what's 396? 198. Okay, I think 2 goes into this again. 99.
3 is 33.
How about 11 and 9?
Ooh, I like 11 and 9. 11's prime. And then, 9's not, though. What's 9? Okay, and then, so it looks like I got all prime numbers now. I'm going to rewrite this in standard form. So there are 2 2s, there are 2 3s, there's 1 11. Okay. The prime factorization of 396 would be 2 squared times 3 squared times 11. So whether you did this with trees or not, okay, so why did I have you do all this stuff? Because you've done this in the past. This is like a pre-algebra thing.
In like 11, like you're in 11.0, and you need to know how to use it.
Yes, and specifically I'm going to show you 2 strategies for 2 like additional things that you do, that you can do a lot, but maybe you weren't aware of. You have a question?
Yeah, why?
So 2 relatively important applications of this prime factoring business are finding greatest common factors and finding least common multiples, which are 2 things you've heard of in the past, but maybe didn't have a terribly efficient way of finding them. We can find the greatest common factor, or just to remind you, the greatest common factor is the largest natural number that divides into each of a pair of numbers evenly. And that pair will be, I'll give that pair to you. That's just the definition of GCF. So just from you should already theoretically have remembered that. Well, there are a lot of ways to find the greatest common factor, and most of you, if I'm not mistaken, will probably just guess and check and kind of hope for the best. Using prime factors, we can actually, there's a really easy process if you already have your both numbers prime factored. So to find a GCF, not just A, but the GCF of a pair of numbers, write all of the shared prime factors then multiply. For small numbers, greatest common factors aren't that bad because we're used to working with little tiny small ones. But for big numbers, it can be really helpful to find the prime factorization and then find all the pairs of primes that are shared between the 2. So for example, if I ask you to find the GCF of 396 and 242, normally that would be a pain and you might just give up right away. Because why would you want to find, how would you find that biggest number? That seems a lot of guess and checking. If you already have them prime factored like we did for B and C, it's actually really, really easy. I want to find just the pairs of numbers that are shared between them. So what's up? One pair of prime numbers that each of these 2 share. Stu, give me one. They both share 11. And how many 11s do they share? 1. This has 1, and it could pair up with one of the 11s over here. Is there anything else that's shared? Caleb? 2. And how many 2s are shared? One of them. This 2 gets shared with one of the 2s over here. Are there any other shared pairs of numbers? Now this only has 2s and 11s, and there's only 1 2 to partner up with, and only 1 11 to partner up with. So that's our partnership. And what's 2 times 11? So the biggest number that goes into both 396 and 242 evenly is exactly 22. There's no ifs, ands, or outs. There's no guessing involved. Find the prime factors, and then find all the pairs that get shared up. Write them down, multiply them together, and you've gotten. And you can construct the smallest or the biggest number that goes into both evenly. We do this a lot, and you did this quite a bit in, I believe, factoring back in chapter 9 too, trying to find pairs of numbers that do special things. So this is an important one. Okay. So there's some examples on the back side of the notes. Okay, actually, I'm going to do all three with you. Okay, so find the GCF of this pair of numbers. So you could either guess and check, which I think some of you, what do we guess and check to get for A? Okay, we think it's 6. So let's use prime factoring to confirm our answer. So let's factor 30. Okay, what's the prime that goes into 30? Okay, 5 goes into 30 how many times? Okay, can we break 6 down? And what is 6 the same as? 2 times 3. So the prime factorization of 30 is 2 times 3 times 5. How about 18? What's the prime that goes in 18? And 6, as we saw before, is the same as 2 times 3. So 18 is the same as 2 times 3 squared. So what's all the shared primes? There's a 2 that's shared. 3 is shared, and how many 3s are shared? Just 1. Is 5 shared? No. So our GCF is 2 times 3, which is, that's exactly 6, what we thought it was from before. Okay, so 315, 315 is, you use a factor tree, or we can just find some primes. 5 certainly goes in, because it ends in a 5 or a 0. 315 times 5 is, or divided by 5 is 63, I believe.
9.
Which is 5 times 7 times 9. 9 can be broken down.
5 times 7 times 3 squared.
So this is 3 squared times 5 times 7. Okay, 252. 2 times, what is that? 126. Okay, what number goes into 1? Oh, I think another 2 goes into 126. 2 times 2, and then half of 126 is 63. Oh, we broke 63 down. Would you mind if I just skipped to the end of 63 that was 7 times 9, which is 3 times 3. Okay. Okay, so what's the GCF then? So 63. Let's see. They don't share any 2s, so I don't care about 2s. They share 2 different 3s. And they don't share any 5s, but they do share a 7. 9 times 7. is 63. So the biggest number that goes into both 315 and 252 is 63. Okay. C is a pretty special case. So 77 breaks down pretty quickly. See, 7 goes into it 11 times. And 11, both 7 and 11 are prime. 39, 3 goes into it 13 times. 13 is also prime. So what's the greatest common factor between 77 and 39? Do they share any prime factors?
No.
No. So if they don't share any prime factors, then what number is the biggest that goes into both? 1. 1. So since they don't share any prime numbers, they do share a 1. So the best you get is a 1. Just for you future math nerds that go on and take math later in life, these kind of numbers are really awesome. The ones that share, the ones whose greatest common factor is 1, have a special name. Those pairs of numbers are called relatively prime. Although they're not prime in and of themselves, they don't share anything in common. That was finding pairs of number, the smallest, or the biggest number that each of these go into, that goes into each of these evenly, excuse me. So we're going to do the other side of the coin. So least common multiple. You've actually found least common multiples a lot, especially if you work with fractions. Okay. Well, one way to make life easier with fractions, if you say have to add 2 fractions together, you got to get a common denominator, right? So we got to find the smallest number that each of these goes into evenly. In this case, it's 6. In the case of a half and a third, it's 1/6. This least common denominator is an application of what's called finding a least common multiple, LCM. Okay? So we can also use prime factors to help find those things really easy. So if I want to find, just recall, LCM, or least common multiple, that's the smallest number each of a given pair divides into evenly. So it's like the reverse. So now we're looking for a number that each of these things goes into themselves evenly. Our LCMs, is the least common multiple ever going to be smaller than the pair of numbers given? It better not be, because it won't be able to make it in. So this, even though it's LCM least common multiple, it's always going to be at least as big as the biggest one that you have.
So what, 30?
Possibly bigger. So what's the smallest number that each 30 and 18 go into themselves? 2 goes into them, but 30 doesn't go into 2. We want a number that 30 goes into evenly and 18 goes into evenly, if you were going to do example A from above. How do you calculate that? Well, if you know the prime factorization, it's pretty easy. If you know the prime factorization, easy. The LCM can be created by taking each prime factor from the given pair. The most times it appears in any one of the numbers. So to find the least common multiple, what we can do is we can look at the prime factors, and we're going to be very inclusive. So we're going to find all the different ones that appear, and wherever it occurs the most in any one of those two lines, we're going to write that number down. In the end, we'll just multiply all those shared prime numbers together, or excuse me, all those prime numbers that ever occurred, multiply them together, and life's good. So an example of this. How about 28 and 15? Okay, well, first let's prime factor these. So 28, that's the same as 7 times 4. 4 is 2 squared. So 28 better be 2 squared times 7. $15, that's a relatively easy one. That's what 3 goes into it 5 times. And 3 and 5 are both prime. So the least common multiple of 28 and 15 is we're going to identify every possible different prime number that we see, and we're going to write down the most times it occurs in any one of the two lines. So let's see, what's the first prime number I notice? Oh, 2. What's the most 2's that I get in any one of the two lines?
2.
2 of them. So I'm going to have a 2 squared involved. Okay, what's another prime number I see? 3. What's the most 3's I find? One of them. Okay, what's another one? 5. What's the most 5's I see? Okay, and what's another? Any more? 7. What's the most 7's I see? 1. So the smallest number that both 28 and 15 goes into evenly is 2 times 2 times 3 times 5 times 7. 420. Now, this was a special pair of numbers. 28 and 15 are the same kind of numbers as we had in example C. Notice that there's nothing in common between 28 and 15. So if you have two numbers that have nothing in common, that are relatively prime, then their least common multiple, just multiply the two things together. It's kind of a cool thing. That doesn't necessarily happen if they're not relatively prime. We always get a smaller number than just multiplying them together. So I think B might clear things up a little bit more. B, let's see, let's factor 18. We did it up here. So I'm just going to copy my final answer down. 18 is the same as 2 times 3 squared. 24, I don't think we've already done. But 24 is what? 2 times 12. Let's see, 2 times 2 times 6. 2 times 2 times 2 times 3. 6 is 2 times 3. So that's what? 2 to the third power times 3. Okay, so I want to know the least common multiple. So I'm going to look at each of these two prime factorizations. I'm going to find all the different primes I see. So what's one of the primes I see? 2. What's the most times I see 2 in any one of the lines? This one. So my LCM is going to have a 2 to the third. Okay, is there another prime that I see? See a 3. What's the most times I see 3? Up here. Are there any other primes that I see? No. So the least common multiple between these two, the smallest number that each 18 and 24 goes into, 2 times 2 times 2 times 3 times 3. 72. So 72. What I want you to do is attempt C and D right now. And while you're attempting that, I'm going to pass out the worksheet that we have for homework.